So let's go. So hi, and thanks for being here in front of your computer, and welcome at my home. I'm going to tell you about the research I've done during the last 4 years under the direction of Stéphane Douady and Pascal Jean-Lopez. The subject is the organism Gorgonia ventalina, an octocoral, but more precisely, its form, its formation, and its deformation. This is far from being the most studied organism. In consequence, I will put the emphasis during this presentation on how we can extract knowledge from the other field to study this organism, and how we can use what we found here for other subjects. But let's begin our journey far from here, where we all are, into the environment of this organism, the Caribbean Sea. So we are on the coral reef, next to the coast and close to the surface, where the water movement is maximal due to the waves. And this biodiverse agitated environment is home for Gorgonia ventalina. This colony that you can see here, plenty of Gorgonia ventalina, is an onthozoa, a fixed class of Cnidaria, one of the earliest forms who emerged from evolution. The colony is created by polyps that you can see here. They are biological units which populate the colony through asexual reproduction. They gather nutrients from the floor and are in symbiosis with the algae, so the Gorgonia can gather energy from photosynthesis, even if it's an animal. And among the genus Gorgonia, Gorgonia ventalina has very small polyps, as you can see on the right, especially compared to the size of a colony here, that can be up to 2 meters and always with a plate shape facing the swell. So, in consequence, even in small wave conditions like this, the deformation is important. There is this beautiful oscillation from one side to the other side. And this oscillation is very important. It might modulate the amount of energy and nutrients they gather. And also, you can imagine what it can be like when it's not the typical tropical weather, but rather a hurricane, which is on top. So it might remind you of this fable from La Fontaine, the oak and the reed. A rigid Gorgonian like the oak will be uprooted because the interaction will be too strong. And a flexible Gorgonian like a reed can survive. But if it's too flexible, then its surface can be projected on the reef and teared up its surface. So for survival, there must be a trade-off between the rigidity and the flexibility, and thus the optimal shape must depend on the environment. The variability of shape, according to the mechanical environment, has already been observed for multiple species. Here, for example, an octocoral, its shape goes from a dense, diffuse shape to this more branching one directed in heavy flow. This relation can be understood with growth mechanism. Organisms are growing from a small structure to a complex final state. And this process is very important. Even if the process is simple, its iteration through time creates the emergence of a property. Here, for example, each layer is like a tree ring created by a simple growth process. And from the bottom to the top, we go up in time, we iterate it. And at first we had a single line, and then we have this complex shape. And the growth process naturally takes into account the environmental perception and reaction. It is, in consequence, a good approach to establish the relationship between an environment and the shape of an organism. So let's go back to Gorgonia ventalina. The growth is going to change the shape, which is going to change the movement, which is going to change the growth. There is a feedback loop. Are the properties emerging from this feedback loop making the shape adequate to the mechanical environment? Well, for a moment, we don't know. And there is a wide variety of shape between colonies. Is this the consequence of the environment? Is it a phenotypical acclimation or just a genetic plasticity? And do these shapes, as diverse as they are, share common properties? And if so, which are the properties? So Gorgonia ventalina is an excellent candidate for a study of acclimation to the mechanical environment. It cannot move nor change to another environment as it is sessile. And the only thing it can change is its shape. So the problem is more relevant for this species than other Gorgonians, especially as it has the thinner structure and the larger surface, so more interaction with the fluid. And especially finally, personally, the beauty of the shapes led me there. The idea that there is information in the organization and that we could get it if we knew how to read it is what motivated me at first sight. So if you zoom in and try to understand the shape, the close detail shows you that it's a network, something especially hard to describe. Using classical allometry based on tree shape, this type of approach tolerates no reticulation nor loop in the structure. And here we have these loops everywhere. So we need new allometry, new method on this shape. And these are parts of the reason that explain why Gorgonia ventalina is often overlooked in research. And also, no growth model that we know can take into account such shape and explain it. So we need to find some new. In consequence, we have this main problematic. How could the shape of Gorgonia ventalina be the consequence of an acclimatation process to the mechanical environment? And we can define more precisely each term, which leads to some sub-questions. How can we describe the shape of Gorgonia ventalina? What is the growth process behind? And what are the properties of Gorgonian which emerge from this process in terms of mechanics? So we are going to explore these entangled problems, form, formation, deformation, through a metaphor of learning a book. We learn the language, then we read it, then we understand its meaning. And first and foremost, we have to determine the language it is written with so that we can analyze it. So when we try to read and to learn a new language, we can look at other languages that are already known. And here we take into profit the relation between species of gorgonians. We can reorganize some of them into a continuous amount of bifurcation and branching. It goes from the trunk to a few branches to what we call the C plume. Then branches and branches, and then it starts to reticulate, creating a few loops in the structure. And then we have this very networky shape, which is the C fans, like Gorgonia ventalina. There is one study that has monitored the growth of Gorgonia ventalina. It's a very slow process, about 3 centimeters per year, and the growth is on the tip, the boundary of the Gorgonia. Here you have 2 contours, which is showing the difference of shape 8 months apart. So we can zoom on the network to understand it. So the shape of this colony is in multiple layers. We have first the polyps. We make the choice not to consider them. And then you have the sclerotic layers, an ensemble of calcium carbonate elements that you can see here. And we can remove it and focus on the backbone of the colony, the Gorgonian skeleton, as it is easier to read. And we can look at this part of the skeleton and especially zoom on the growing part, the tip. So on the tip, we see branches that are growing like a tree shape. And the first thing we observe is that the tip, which extends with the growth, is kind of leaving a trail of the skeleton. So all those positions were the position of a growing tip before. And this extension of the tip process is creating continuity. We also see that branches are creating other branches as bifurcation. They start perpendicular and then go into a direction. There is a tropism phenomena. And these branches will eventually collide on each other, creating some reticulation. So hence, we have 2 types of intersection, in green bifurcation and in red collisions. There are 2 kinds of nodes in this network. And colliding branches reticulate are creating the reticulation of a structure and stop their growth, hence the reticulated shape. And this organization is conserved even if we zoom on the middle of the shape. So we have the same local pattern, but at another scale. And collisions stop the growth and give information on history events. A branch who collided on another one arrived there later. So it's already an information on the story. Skip a slide. And if we integrate this approach, we find that the shape of sea plumes that I showed you before can be found in sea fans thanks to this mechanism of reticulation. And there is also another phenomenon, reinforcement, that you can see here as white thick branches. These reinforcements are never on the tip, nor they don't follow the continuity of the growth, yet they are continuous. Hence, we will consider them to be another process that we will explain later in this presentation. We will, for now, focus on this. So, what I've presented you is an ensemble of description, and we can use it to compare gorgonians. But to do that, we need to go to quantification, to allometry, a reduction of the shape to a few well-chosen number, easier to manipulate. So we need to extract the network using this idea of continuity. And as this network contains a huge number of elements, we need to tell a computer to do it for us. But first, let's take into profits what the others have done elsewhere. The idea of continuity in a network, we experienced it every day when we commute in a city. Well, not during a lockdown, but we think in the city, in streets, not in terms of crossroad. We think with continuity. And doing network analysis using this idea lead to powerful indicators of a city. So it's a good source of inspiration to try to expand it to gorgonians. So in consequence, we are using the same vocabulary. An arc is a spatial edge of a network between two crossroads, one portion. And a ways is an ensemble of arcs locally connected with a continuity in the direction. So the arcs are kind of the letters of our words, and ways are the words. So our need is to go from the picture to a network of ways. This is not a simple problem, and actually it has been the biggest and longest part of my work, trying to succeed this step. We succeeded and created a Python library that you can use for any problem of continuity in a spatial network. I will simply tell you here the essential step of the construction, then focus on what it allows us to understand. We begin with a high resolution image of a colony with a clean background. Then we extract all the contours. We can do analysis of a property, but most information we get here is either irrelevant or correlated to more elegant approaches that I'm going to show you. So we extract the arc network. We take all the points of at mid distance between two contours, and we use them to construct the arc in red, and we recreate this ensemble. But the bigger the ratio between the width here and the length of branches, the harder it is to extract this network. You can see that you have some bubble and deviation effects. And so the bigger is this ratio, the harder is the reconstruction of the network. So how bad it is? Well, quite a lot. All the points in red area are badly placed and need correction. We have mostly worked with AG images of colonies with the sclerites because we didn't want to destroy the colonies. And even if with this difficulty, we can still do it. It's just harder, but I'm very stubborn, so it's okay. What we do is that we take the intersection between arcs and we calculate a score on the alignment of arcs 2 by 2. And we take the best score as the alignment. The best criteria we found is to propagate a line between the arcs and look how far it can go on the structure. And with this 2 by 2 intersection, we reconstruct the ensemble of ways. And the way network is back with continuity. And this is a very fast process, about 30 seconds, in fact. Yet it is imperfect for some association that we correct by hand, which can take about 1 hour per gorgonian because there are a lot of places. And we did this process on 24 gorgonians, along with 15 other structures than gorgonians, so that we have a wide samples of shape to describe. And then what we do is what we are going to try to extract information from this, reduce it to few numbers that we can compare. And we are going to do that. And as gorgonians in our description are described as an ensemble of ways, and ways described as an ensemble of arcs, we can look directly at the number of arcs per way. Are most of the way of the same number of elements? How is the number of length distributed? Actually, there is an equivalence between this number of arcs in a way and the number of connection to a node in a classical network, which is called degree, and is an excellent indicator of a network structure. So here we have a way of degrees of 6 arcs, hence a degree 6. So we color each way according to its degree, and we can look at the number of ways of the same color. As there is a wide variety of values, what we are going to do is represent this distribution in log-log axis. And if we do that, we found a power law distributions on 2 decades. It means that there is no scale in the system. The growth is modular, and that only one number is enough to describe this distribution, the slope A. So it's efficient to be compared. And we would like to understand how such distribution can appear. So we look at the distributions of ways which are still growing with no collisions. So we can do that. Here, the bold branches. So for the pleasure of variety, I took another Gorgonian. And if we represent only, we take into account only these ways, the growing one, and we find another power law, but with a slightly different coefficients. So that's really surprising. And what we should do when we see such property and check if we have done cherry picking, just taking the nice shape to get various results. So we test it on many Gorgonians. And what we found is that if we represent all the distribution normalized on the same graph, they all coincide. There's definitely a trend here. So all this distribution correspond to power laws, but with slightly different coefficients. So we can look at the distribution of those coefficients and compare them. So each Gorgonian is a point with in abscess, it's the full coefficient of its distribution. And then in ordinate, the coefficient only corresponding to the growing ways of its shape. There seems to be mostly a constant difference between 2 coefficients, and which is about a factor half. And there is absolutely no correlation between the size of the shape, the size of a Gorgonian, and its coefficient. It's invariant during the growth of each Gorgonian. So we said that we had the numerical version of our networks. Is it our special properties of Gorgonians, or is it a property of a wider range of shapes? So we tested on desiccation patterns that are obtained with a drying process of clays that Philippe Bonin did as experiments. And on those experiments, the distribution of weight is following this power law too. And it's also the case on dragonfly wing we test, yet with a small twist that you can see here, or big twist on 1 degree ways, which is a sign that there is another growth process in fact. So the same type of distribution has been also observed on the degree of cities with the same type of value for the slopes. So the shape of Gorgonia ventalina, according to this indicator, belong to a more general class of mathematical objects, and they all share in common an idea of iterative construction with ways. So, in fact, power laws are really important as they can be found in many different domains, some impacting profoundly our life. It looks like most of them correspond to the rich get richer logic and process. Understanding how such laws are created, what process leads to it, is an excellent way to characterize the dynamical process behind the structuration of such system. But for now, there is no known creation process with true power laws, as we've seen on Gorgonians, nor a process that gives power law that we observe with the qualitative elements that I've shown you before. So it's opened some new approaches and new results to understand such structure. But the network can have a function. So with the interactive element. So instead of attributing a value just on one way, we can look at values according to interaction between ways. So we can look at one of these examples, looking at the whole sentence. So the one I would like to show you here is the measure of hierarchy. So the idea of hierarchy is the minimal number of turns on the network you have to do to be on a way from one point. So here are 2 examples to explain it. So you come from here and you count the number of ways you have to go through to go on this way. So for example, 1, 2, here 1, 2, 3, 1, 2, 3, 4, here 1, 2. But if your reference point is somewhere else, then this score is going to change. And what we know is a perfectly hierarchical network from 1 point is going to give you a distribution as a Gaussian with no fit parameters. It's just one distribution only depending on the number of ways. So we know that Gorgonia ventalina is growing for a little points at the beginning, the foots. So we can look at the distribution according to the foots. And what we see is it's not working. Yet, if we suppose that the network is structured from the growing branches and we set them at reference points, then we have this Gaussian distribution, which is found with no fit parameter. And if we test it on many Gorgonians, it works always at the same time. It works always perfectly, but it's not working when we have badly numerized the network. So it's a sign that it's really a property of such network. And it's surprising because we expect it to come from the foots. And actually, this phenomenon can be explained through collisions. And this is what we are going to see with the logic of a plume. So not always has been created equal. This is one branch with all the branches it has directly created through bifurcation. And if we take all this sub-ensemble of a shape and we look at the distribution of the degree, we can see that here we have a cluster, all these values going together, and here we have some outlier to this distribution. And it's interesting because this cluster corresponds to an envelope around the way, the main branch of the plume, and the outlier, in fact, are kind of creating their own plumes on the structure. So we can decompose all these structures in a few plumes. And when we do that, we directly access to one precious information, which is when are the plumes created and when the plumes are stopped. And those collisions that stop of the growing process explain why there is no Gaussian structure on the foots. And a plume, especially, can only be stopped through a longer path in the network. So for example, if you come from here and you have to go here, this path is shorter than doing this. So it's giving information on how fast are the branches growing. And with, so it's another type of information. And with this approach, we highly reduce the number of elements to take into account in the network without losing any information. So we can translate even big Gorgonians like this one, which is more than 9,000 ways, into almost entirely all the structure to less than 100 plumes. And those plumes are in 2D to describe a 2D surface. They have a direction, so we can do tropism studies on them. They have a width, which is going to vary. They have a creation point, they have a collision point, and they have 2x2 interaction. There is no blind spots according to the properties we have saw before. So in my opinion, this is what should be the future of allometry on Gorgonia ventalina. And if we had more time to work on this subject, this is what I would analyze. But yet I found it quite far in my thesis, so I decided not to go further. And this notion of plumes is also linking the network to the mechanics and allow us to understand the deformation, as you will see in a few minutes. Let's take a look back at the general shape. We have not talked about something. There are some splits in the shape that you can see here. We observe them within one colony, but also between some colonies when they are quite close. When you are in the lab in France and look at the flat shape of Gorgonian, it's hard to understand how, what, and why is there such split in the shape. But we can understand it by looking at them in vivo. So here we have a view of a Gorgonian upside down. And what we see is that when a Gorgonian is deformed, this open shape is closing. And thus, the deformation is in 3 dimensions. which is something impossible for a plate. So this shape here is more aerodynamic than what it could be if it could only be on a 2D deformation. And moreover, we can see, for example, on this sample from the video I've shown you before, that the movement is desynchronized. So there are some new properties, but the question is, how do they appear? Well, this mechanism can be understood as an equivalent of the crown shyness you can observe in forest. When two tree movements are out of synchronization, they are going to touch each other on the crown and creating mechanical stress and inhibiting the growth. And we observe that the split creation always occur at the divergence between two plumes. So the two branches which are trying to reticulate are no longer synchronized because of the lack of elements in the network to synchronize them. And so instead of just creating a reticulation, they are going to add strain on each other and to add collision and stress, which is going to inhibit the growth. And we can see that before the creation of a split, we always have stress marks on the structure. So we can understand the creation. And actually, this closed shape that we observe can be thought like the Africa and South America shape correspondence, but here with deformation. And because of this, we can read from the deformation profile, from the split profile, a deformation profile, a typical curvature. And we can also link a deformation to the rigidity of the structure and the force exerted on the structure and its distribution. And with all this idea all together, it would mean that one could theoretically extract a characteristic spin of the environment by simply looking at the shape of a gorgonian and its reinforcement. So, as you might have seen, we have gone continuously from the network to the mechanical properties, the deformation. So it is time, with our understanding of the growth, to measure the mechanical properties, the reinforcement properties, and deduce this idea of acclimation. Oh, let's do just a little bit of theory. We said that the force created by the flow on the structure is important, which is this formula, and we can link everything to it. The force transmitted to the reef is equal to the fluid density of water with the exposed surface, the surface of a gorgonian facing the fluid uniform speed far from it to the square. That's why strong speed are so important. And also a drag coefficient. This drag coefficient is going to take into account all the specificities of a rigid shape. For example, a very streamlined shape, like a wing shape, has a very slow coefficient, and a non-aerodynamic shape, like a plate, has a bigger coefficient, about 1.5. But this theory is only working when your object is rigid, and it's not the case here. The shape is going to change according to the speed as it differs, and the aerodynamism is also going to change. So what we do is we use this approach called reconfiguration process, and we take into account all this variation of u here into one coefficient that we call the Vogel coefficient that we apply on the speed. And so the measurement of this Vogel coefficient is going to take into account all the information of this deformation and reconfiguration process. It has been measured for a wide number of subjects, especially for vegetal shape. So let's calculate this kind of things on a gorgonian, this coefficient and the drag coefficient. So to do that, we set up an experiment close to gorgonians in Guadeloupe. We want a controlled environment and reproducible results. So we place ourselves in a swimming pool instead of in situ, so we can master what is happening. And we reproduce a water movement, not by moving the water around the gorgonian, as it will be very complex to put in place, but by moving the gorgonian in still waters, in the referential of the gorgonian. It's a good approximation of the movement, and it's way easier. So we place the gorgonian on a trolley that you can see here or here, and we link this trolley to some weights, like here. And we are going to put some weights, and the weights pulling down are going to push the Gorgonian on the sides and create a force. And so we transform this vertical movement into an horizontal one. And so we can move the Gorgonian and master the force applied to it. We measure the trolley speed here, which is an equivalent to the flow speed. And we measure it with a camera. And we also put an embedded camera with the Gorgonian to look at how is it deformed. So the way we extract the data from this experiment is that we want the drag force and the speed. So the drag force can be calculated with the weight values we applied, and we remove simply the frictions. And also we put some calibrated force captor on the structure to get the signal. And to get the speed, what we do is we take the video of this movement, and from this video, we extract the position of the trolley. From this position, we extract the speed, and then we synchronize both signals. And from each run, we extract the steady speed when the speed is not moving, the maximal speed, and the force corresponding. And so it's giving us 1 point at each experiment. And we can do that for each Gorgonian. We also extract the deformation signal. What we do is that we simply look at a perpendicular view and extract one profile that we fit with what we call Bezier line, which are very efficient to take into account smooth deformation and curvature. So when we do that, we can have a profile of oscillation, as I showed you at the beginning. And also, if we synchronize this, we have a link between the force, the deformation, and the speed. And what we do is that we do this approach on many different Gorgonians from 2 sites in Guadeloupe. The first one here has a huge exposition to the ocean swell. So large, long period and large amplitude waves. And this spot, which has close wind-driven waves, so small amplitude and small frequencies. We take 10 Gorgonian per location with size varying from 10 centimeters, this small one, to 90 centimeters, some big one. And so we do for each Gorgonian 20 runs with weight, so approximately 400 runs. And we divide, we can represent all the points on the same graph, like here. We divide, in fact, each force by the surface. So we can just measure the drag coefficient and the Vogel coefficient. And here we have 22 Gorgonians, and they mostly collapse on one curve. So we could read the main Vogel coefficient as the slope and the height as the drag coefficient. So from each Gorgonian, we extract these 2 values, and we reduce them to these 2 values. And what we see is that we have these 2 coefficients which are not varying nor from the size nor from the location. So it's not depending on the shape nor of the location. And moreover, we can understand the value of this coefficient according to literature. In fact, this CD of 150 corresponds mostly to what we expect from a rigid plate. And this Vogel coefficient of minus 0.90 mostly correspond if we look at the reconfiguration theory done on beam in uniform flow. It corresponds mostly to a fan shape, which is going to enlarge with very little reinforcement. So this is describing the shape and the mechanical properties of Gorgonians. And we can go a little bit further. If we add artificial splits or cuts in the structure, but without cutting the reinforcement I told you about, it's not going to change the value of these coefficients, nor the deformation profile. So it means that it's really the reinforcement which are structuring the deformation and carrying all the signal, all the constraints, and that the split shape and the reinforcement shape are correlated. And if we look at each speed force graph for Gorgonians individually, we can see that for slow speed, they don't reconfigure, but after one's characteristic speed, they start to reconfigure. And that this speed is mostly the same for every gorgonians. And if we go back to the reconfiguration theory applied on a beam, we can extract this characteristic speed from the Cauchy number. And this characteristic speed can be written as an ensemble of material properties, which are the same for every gorgonians, and also a quantity which corresponds to the shape of a gorgonian, especially it corresponds to the thickness here, which is an equivalent to the width of reinforcements. So if this quantity is constant, it means that there is a relationship between the width, the length, and how reinforced gorgonians are. And with this information, if we add it to, with this growth invariant, if we add it to the theory of a uniform beam in an oscillatory flow and the data from the amplitude frequency relation for shallow water waves, what we see is that larger waves and larger gorgonians are going to have slightly different oscillation. They are going to have an out of inertia and momentum accumulation of the movement. And this is creating shocks. This is creating huge momentum transfer to the foot. And this could explain why gorgonian can be uprooted as it creates shocks on the reef, and why we observe some uprooted gorgonians after hurricanes. Yet this approach has 3 blind spots. The first one is that the reinforcements are non-uniform on a structure. So how these reinforcements are dampening the shock. The second is that the splits are is desynchronizing the movement, which is dampening the effects of shocks. And the third is that the fixation of a gorgonian of the reef is evolving with the shape. And so this is something we should take into account if we want to go further to understand really this kind of phenomenon. But with all of that, we've seen many facets of gorgonia, of its shape, of its formation, of its property, and of its deformation. So how do we understand that after 4 years? Well, just a bit of water. At first, we were kind of lost. We had a lot of direction to explore, but we needed a map of the different concepts, how they are linked. So we identified all the concepts that could allow the description of the shape that we saw together, the continuity, the bifurcation, the collisions, and this creating the reticulation, that we had some splits, that we had these deformation effects, and that we had a mechanical environment with waves. We saw that the best way to describe this now is to use an allometry of Plumes, as they carry all the properties we are looking for here. And then we also studied how the concepts are linked, how they interact. For each of the link, we have created a model, measure, or description of a process. But what is interesting is how the properties emerge from this big loop. Reading one process in silo cannot give you the whole picture. And this is why I insisted on the description of the whole story of a systemic view of gorgonians. And we have measured many properties emerging from this loop, have shown you the two power loss degrees, the Gaussian hierarchy, the closing splits, the mechanical reconfiguration of its invariant. And mostly what we can understand is that we have 2 or 3 processes in the growth. A primary growth in elongations, which is short-term and extensive, making the shape grow. This alone will be very dangerous as it will easily bend the gorgonian. But we have also this secondary growth with the reinforcement on the long run, which is intensive. It doesn't extend the gorgonian, and stabilizing the mechanical properties. And this idea of 2 mechanisms can be also found in the plant growth strategy to acclimate to mechanical environment. So we have a convergence of strategy according to the function of a shape. And the first one is growth, and the second can be seen as an acclimation mechanism. But here we have another specificity. This specificity is the split creation mechanism. And it could be this mechanism that allow really the acclimatation thanks to the streamlining and desynchronization effects. And the origin of this mechanism is quite funny, because it's that the reticulation that defines the shape of gorgonians is not always occurring. And what it doesn't, it's what creates the splits and what creates all these properties. So there's no need for a very complex process behind the split creation, and they create a lot of properties. So now, once we are here, there are many things we can do. We can go deeper into each relation of a map, of this map. We can complete this map. We can find the biological mechanism related to each logic, to each function. We could improve the mechanical concepts that we use on gorgonians to take into account the desynchronization and the non-uniformity of reinforcement. We could exploit the allometry of plumes to correlate the shape with ecological measure of the environment that we couldn't do during this phase. And there are many more things to be discovered. And I think using this representation could be useful for anyone who wants to study Gorgonia ventalina, as it is a same basis to understand the properties of this complex system. And also, we can also use this approach of a map to understand complex system to look at other Gorgonians. But for me, the most essential things is to draw these maps of complex system, to ask how they function, and deduce from this whole question in the map all the what and why question. It's, I think, the best way to tackle with the complexity of systems. And this feedback loop between entities and mechanism with an overall acclimation of fitness core emerging from it correspond to many problems from our society, from other things. And we mostly explore primary growth as a society. And it might be time to understand how we can use a secondary one to acclimate to our environment, which is quite a big problem, as you know. But this is another story for later. What I would like to finish is that I wasn't alone during this time, and all of these people helped me so much during this thought research. Of course, my two directors, but also people who are behind, who worked with. You saw Julien and Mick just before, who were always every day here to help me and bring me joy and bring me motivation. And also Claude and Sebastian, who helped me to do all the manipulation in Guadeloupe and all the measure in situ. And Paul, which did some work in internship. Of course, I would also like to thank the best room to work, I think, that could ever exist, which is the 9/11 for the ones who know. And all the people who were in it, Tanguy, Mathieu, Solène, and so on, all these fantastic people who helped me to spend 4 fantastic years. And as we are all the consequences of a growing process with many people interacting with us, I think I became interested into research and passionate about this and confident to continue into research, thanks to those people, especially all those people who taught me about physics and the fantastic beauty of understanding the properties of complex system. And of course, Pauline Smith, who is just right there and helped me to do all of these things during those 4 years. So if I've done my work well, now you can read this book. You can understand the properties of this complex system. And you can, from all the concepts we've seen, find all the information which are behind. And if I have done that, I think that I'm satisfied with a little bit of what I've done. So thank you for listening.